All right, guys, so here is your starter from earlier. And I have filled in the definition of a rational function, a function of a polynomial as a numerator and denominator, p of x, q of x, where q of x, the denominator, cannot equal 0. And I have factored the expressions you were supposed to do for your starter, but I haven't simplified yet. So let's simplify. All right, in A, this x plus 2 is in the numerator and denominator. So these can simplify. And let me move down a little so I have some space. And now this is 1 over x minus 5. All right. Number 2, none of these factors match up. So this can't be simplified. We'll leave it as is. C, we have an x minus 4 in the numerator and x minus 4 in the denominator. So this simplifies to x plus 1 over 1, which is really x plus 1. All right, so we had our starter to help us remember some factoring skills. Now let's use this information. Now, we've actually looked at domains of rational functions already in previous lessons. So let's just quickly review that to use the rest of our lesson. To find the domain of a rational function, what we need to do is we need to factor the denominator. And really, we have to set it not equal to 0. Solve for x, and these values, x cannot equal these values. These values cannot equal x. That's why we use the not equals. Cannot equal x, and are not in the domain. And all the remaining values are. So let's see. Let's find the domains of these rational functions. All right, so we have x plus 2 over x squared minus 3x minus 10. So we just factored the denominator according to our directions. So let's see, this denominator we need to multiply to negative 10 and add to negative 3. Let's see, I think that's x minus 5 and x plus 2. But this seems a little familiar. I feel like I factored this recently. Right up here in our starter. That's the same denominator. In fact, it's the exact same problem. And we can see B is the same problem and C is the same problem. Oh, so we've already actually factored all of these. How nice. And by the way, this should say A. So we've already factored all of these. So some of our work is done for us. So now what we do is we set this not equal to 0. We solve for x the same way as if we were setting equal to 0. So x minus 5 does not equal 0. X plus 2 does not equal 0. So x does not equal 5 and x does not equal negative 2. These are the two values that x cannot equal because they will make our denominator 0. All right, so I'm going to write the domain. I'm going to use set builder notation because when we have not equals, it's hard to use things like list or integral notation. So x such that x does not equal negative 2 or 5. Okay. All right, second one. Again, we've already factored this earlier in the starter. This was x plus 1, x minus 1. Set this not equal to 0. X plus 1 can therefore not equal 0, and x minus 1 cannot equal 0. And x cannot equal negative 1, x cannot equal positive 1. And again, we'll have our set builder x such that x does not equal positive or negative 1. Last one, no factoring necessary for the denominator, just x minus 4 does not equal 0, and x cannot equal 4. And again, set builder x such that x cannot equal 4. There we go. So finding domains, not so bad, just have to care about the denominator. But like again, like I said, we've kind of already done this. So like, why are we doing it again? And now you will find the reason that we are doing it again. So if we look at the next page, how do we determine the vertical asymptotes of a rational function? Vertical asymptotes, remember, are those like dotted lines. So let's say like you have a graph of a rational function. Maybe you have a graph of a function that's like this. You're going to have a vertical asymptote. Just like that. How do we determine where these are? And that's actually going to have a lot to do with the domain and simplifying rational expressions. So what we do, we have to factor the numerator and the denominator. Simplify any remaining factors in the denominator. So really anything remaining in the denominator. Set equal to 0 and solve for x. This will give you your vertical asymptotes. So let's look at our examples. Again, we see the same 3 problems as before. And again, that should say A. I should fix this formatting. All right, same 3 problems. So according to our directions, first, factor the numerator and denominator. Luckily, we've already done that in part A. So the factored form is x plus 2 over x minus 5, x plus 2. And it says to simplify, which we again already did in our starter. So this is 1 over x minus 5. All right, anything remaining in the denominator. I didn't spell denominator correctly up here. Why didn't you guys tell me? All right, anything remaining in denominator. There we go. Set equal to 0. So x minus 5 equals 0. Solve for x. So x equals 5. This is our vertical asymptote. All right, same thing for b. Now remember with b, even though we factored it, nothing could simplify. Oops, x minus 1. So we will still do x plus 1 and x minus 1 set equal to 0. This means x equals -1 and x equals +1. These are our vertical asymptotes. There we go. Last one. This one, when we simplified it, let me look back at our starter, we got x plus 1 over 1, which was x plus 1. Do we have anything left in the denominator? We don't. So since there's nothing left, what happens is there are no vertical asymptotes for this function. You have to have something left in the denominator for a vertical asymptote. All right, so now you know how to find vertical asymptotes. But this is not the only kind of asymptote there is. Even though vertical asymptotes are the discontinuities, there are other kinds of asymptotes that don't cause discontinuities. They allow a function to be continuous. And one such asymptote is the horizontal asymptote, which you have heard about previously in algebra and algebra 2. So how do we find horizontal asymptotes? Again, this is going to be very similar to finding domains and to simplifying rational functions. But there are a couple of like weird rules about this one. So the things to apply to all of these. First, we have to determine the leading terms of the numerator and denominator. So determine leading terms of numerator and denominator. is not working because I've got those three bubbles at the top. Denominator. Get rid of everything else. We only are interested in the leading terms. Simplify the leading terms. So simplify the rest. Now there are three things that go on. One, if x is left in numerator, and I'm going to shorten numerator, no horizontal asymptotes. 2, if x is left in the denominator, horizontal asymptote is y equals 0. And then 3, if no x's are left, the horizontal asymptote is the simplified term. So let's take a look and see what this all means. Let's look at our three examples again. So first, determine the leading terms of the numerator and denominator. Now the leading terms, if you don't remember, are the x terms with the greatest exponent. So in A, the x terms with the leading exponent, we have this and this. These are their x terms and the greatest exponent. We get rid of everything else. We don't care about them. And we just take these two terms. So x over x squared. Now this simplifies because this is really x over x times x. And these x's can now simplify to 1 over x. All right, we have simplified. And now let's see which of our three situations this matches with. Where's our x? It is in the denominator, so this is situation 2. And according to situation 2, if an x is left in the denominator, the horizontal asymptote is y equals 0. All right, let's look at another example. So B, we've got our leading term of x squared and another leading term of x squared. And we just take these two, x squared over x squared. If you have something over itself, this is equal to 1. All right, so let's see. We don't have any x's left. Which situation is this? It's situation number 3. No x's left. The horizontal asymptote is a simplified term, which is 1. So y equals 1 is the horizontal asymptote. All right, last one. Let's see, leading term, so the greatest exponent, we've got a squared, and then we have an x here. So x squared over x. This simplifies to x over 1. Okay, so here are x's in the numerator, and that matches with situation 1. If x is left in the numerator, there are no horizontal asymptotes. There we go. All right, so now you have your chance to practice finding these asymptotes on your own. There are 2 more pages to the packet. I do know that a couple of you have a push, I believe tomorrow, so good luck on that. I am giving you through the weekend to complete this packet, so just turn it in by Monday, 8 a.m. There are not a whole ton of problems, but it is like kind of new material. We haven't looked at this previously in the year. So please reach out to me through email or through Google Meet if you have any questions. All right, good luck on your AP tests, and let me know if you need anything. Bye.